So the class of today concerns a technical issue in infinitesimal calculus. It is called the Laplace method. This is a method used to estimate integrals, and it is widely used in physics, quantum mechanics, diffusion theory. It has also see a lot of development in analysis. So let's discuss the goal of the Laplace method. The Laplace method designs an ensemble of recipes to estimate, when we have an integral over a domain of a function, let's say f of x exponential minus a function psi of x divided by epsilon, and we can integrate over the volume dv of x. So suppose omega is a domain in Rn or a manifold, f and psi are sufficiently differentiable functions, at least we assume that they are as differentiable as we need. And so the goal is, instead of computing this integral, to look at what happens when epsilon is small. So when epsilon converges to 0, we would like to find an estimate of this, and to see that this integral can actually be estimated by just computing the function underneath the integral sum at some specific ensemble of points. So this will be the question, is how to estimate this quantity. So for this, let's start in dimension 1. So in dimension 1, if we consider in interval AB a function which has a single minimum inside at a point C, then basically the idea of the method is to replace, when we compute exponential of minus psi of x divided by epsilon dx, is to understand that when epsilon goes to 0, what is selected in this process is the point where the function psi achieves its minimum. Let's call it at C. So for this, we can always write this as minus minimum of psi divided by epsilon multiplied by exponential of minus psi minus the minimum of psi divided by epsilon. So I have done exactly nothing when I have rewritten this integral, but now we understand what needs to be calculated. So this quantity now is given. Minimum of psi is psi of C over AB. And so what needs to be calculated now is this integral, so which we are going to do in in the next slides. So again, what we need is to calculate the integral from a to b of exponential of psi minus the minimum of psi divided by epsilon psi of ix dx. And for this, if we use a Taylor expansion, assuming that at the minimum the function is not singular, and it generically can be written as psi of x equals the minimum of psi. Since this is the minimum, the first derivative is 0, and then we are left with the second derivative. So this is psi second at C, the minimum, divided by 2. And we can always write it x minus c squared plus O of x minus c. So Then what we should do is just to replace. So we can always write now this quantity as, so I will write it formally as integration from a to b of exponential of minus 1/2 of psi second of c of x minus c squared plus, so we can always write this, let's say, in the neighborhood of c. So I will write it c minus eta and c plus eta. And then we can always write the integral from a to c minus eta plus c plus epsilon b, and eta is small enough. Where here we do not change anything, we just write the same quantity. So we assume that psi second of c is not 0, which is strictly positive. Otherwise we have to go to the fourth order term, and then the analysis is quite similar, just the exact dependency in the parameter will change. So this is here divided by epsilon. Okay, so now we can focus on this integral. So I will leave, it's not very hard to show that this quantity and that quantity are actually exponentially small, because outside c minus the difference, the minimum of this quantity in the interval a c minus eta, this is strictly positive. It's actually a quantity that we can call it c1, which is strictly positive. So this can be bounded by exponential minus c1 divided by epsilon multiplied by a constant c2, and again this is a constant c3 exponential a constant c4 divided by epsilon. So which means that each of these terms here goes to 0 exponentially. Okay, so now what we need is to estimate this quantity, the first one. Let's call it 1. And 1 can be rewritten using a change of coordinate, which we will call u. We'll write u square equals second derivative x second c divided by 2 x minus c square divided by epsilon, so that u equal square root of psi of second derivative at the point c to epsilon, and this is x minus c. So we now can write this is exponential of minus u squared. By definition, du is, dx is simply du multiplied by 2 epsilon psi second of c, and with a square root. So we can always put here absolute value, doesn't make any difference. And then we have to integrate. So when x equals c minus epsilon minus eta, we got here minus eta psi second c divided by 2 epsilon, and here we have eta, the same quantity with a sign plus, divided by 2 epsilon. And now we know, so this is a term that depends on epsilon, and as epsilon goes to 0, I epsilon behave like the integral from minus infinity to plus infinity. So this is minus infinity to plus infinity of exponential minus u squared du, and 2 epsilon psi second c square root. And this quantity the integral from minus infinity to plus infinity of minus u squared du. This is by definition the earlier integral, which is square root of pi. Okay, so now we have just shown in summary that the integral, so to summarize, the integral from a to b of exponential minus psi of x divided by epsilon dx behave like pi epsilon divided by psi second of c square root as epsilon goes to 0, and here we had to multiply by exponential minus the minimum of psi in the interval AB divided by epsilon. So this is the behavior of this quantity, plus a term that are exponentially small, plus exponentially term that are of constant divided by epsilon. Actually, we should have written this a bit differently. Let me rewrite it. So this is the term here. This is plus exponential small term of constant divided by epsilon, which can be neglected, and this is exponential of minus psi divided by epsilon. And so basically we would like to generalize this formula in dimension n. So before, it's not difficult to see that if we have a function that is not a vanishing function g of x exponential minus psi of x epsilon dx, and when epsilon goes to 0, the behavior is like epsilon psi, the same quantity as what we have seen, and then we have to add this j at the point c, plus so this I will now just write the leading order term, exponential minus minimum of psi divided by epsilon. If the function j actually is 0 at the point x minus c, so we have to look at the expansion, the Taylor expansion, and look at the first n for which it is not 0, and then usually we have to integrate by parts sufficiently enough, and so we can apply the Laplace formula. This I will not do it here. Another thing that I'm not going to do, but this is not very difficult, is that the so this is one result, second result, and the third remark that I will make, is when the maximum is not achieved inside the domain, but on the at the boundary here. So we have a and b, and in that case we should not do a Taylor expansion of psi at second order, but just at first order, so that we can write psi of x equal psi a plus psi prime a x minus a plus small o of x minus a, and then I invite the person interested in just recalculate the entire integral here and stop at the first moment. So this is this will lead to a different calculation in a different power. Instead of having square root epsilon, it leads to just epsilon, and instead of the second derivative, we have here the first derivative. So I leave this as an exercise. So now let's discuss the general formula. So in dimension n, so we would like now to calculate, so in dimension n, so we would like to calculate the integral of exponential of psi of x divided by epsilon dx. So I assume there's a domain in Rn. This can also be done on the manifold, Riemannian manifold. So basically what we have seen from dimension 1, what is important are the place of the minimum of psi, but in higher dimension, those places can be very complicated. So I'm not going to describe here the simplest case, which is called the case of the Morse function. So psi is called a Morse function. So basically it's a generic case where we assume that at the minimum, first of all, the second derivative exists. So in higher dimension, this is called the Hessian. So we looked at the second derivative of psi with respect to a coordinate system xi, xj, and we assume that this matrix is non-singular. So the determinant of this is not 0. And moreover, we assume that the point where psi achieves its minimum, it's an ensemble of discrete points. So psi achieves its minimum at an ensemble of points P1, PQ, where we assume that the Hessian is non-degenerated, so the condition star is satisfied, such that the condition star is satisfied at each of those points. That is the determinant of the Hessian at the point pk for k from 1 to q. This determinant here is non-zero. So we have a positive definite matrix at this point. And so of course we can use then a Taylor expansion and write psi of x near those points. It's the minimum of psi plus the first, the differential is 0, and now we have to use the second derivative. So since we have psi is at least C2 or sufficiently differentiable, we can always use a frame which is orthogonal and from which the matrix is diagonalized because it's a symmetric matrix. So this is symmetric, and so the eigenvalue are going to be called lambda 1 at point, let's say, pk, lambda 1, lambda n. So that are the eigenvalues of such a matrix. So we can always write it in the form of sum of lambda I. So it's 1/2 lambda I at point pk xi squared plus a term which is negligible, x squared, where we have assumed here that 0 is the point pk. So here x1, xn, it's a frame at the point pk, where the origin is pk. And we can use this Taylor expansion at the neighborhood of each of those points. So now we can take a ball around each of these points of radius eta and consider the ensemble of all these points. And so now we can separate omega as the union of this ball, union omega minus the complementary of the union of this ball, bpk eta. So now we can rewrite the integral over omega of exponential minus psi divided by epsilon as exponential of the minimum of psi divided by epsilon, And now we use the integral of all of these distinct ball. So the intersection of this ball bpk eta of any of two balls is 0. So there is no intersection. bpk do not intersect. So now we can then write the integral of this ensemble as the sum of the integral of b pk eta exponential. Now we can replace psi minus the minimum as minus 1/2 of the sum of lambda I pk xi squared divided by epsilon dx1 dxn plus a term that we have seen, and this is the same as in dimension 1, which is exponentially small in epsilon. There is a constant here. So now let's focus on this term, the first one. So we would like to calculate the integral of a ball of radius eta around any of these point pk of exponential of 1/2 of the sum of lambda I, which are the eigenvalue at point pk xi squared divided by epsilon dx1 dxn. So in here we can always actually change the ball such that, and we should remove basically we should approximate this ball by squares so that we can do the integral. It's going to be much more nicer. Instead of looking at the ball, you just look at the square here. And so the difference between the ball and the square are, of course, the part here, which can be shown to be negligible in this calculation. So this I will assume that now the ball, I will reduce the ball and just calculate everything on squares so that I can transform this integral. So this is the same as the integral over balls of size minus eta n times. And now we can just actually write this as the product of integral of lambda I pk xi squared divided by epsilon dxi, and we end up having a product of 1 to n. So now we simply get minus eta, or what we used to have in dimension 1, which is lambda I pk divided by epsilon xi squared. Actually, this is not exactly the product because the lambda I are not necessarily all equals, so we can write it this form from 1 to n. And as we have seen before, this is simply pi divided by a lambda I epsilon, and then we have a square root. And I think there is also a factor 2 that we have forgotten here, which should be added in here. So now we have this, and this has to be multiplied by n, not n, but this is the product. So this is n times, so this is lambda 1, etc., pi 2 divided by lambda n. So now when we do all this product, we get 2 pi epsilon n divided by 2, and then we got here the product of lambda 1 lambda n at the power 1/2, which is the 2 epsilon pi n divided by 2 square root of the determinant of the SCN of psi at point pk, and this is to the power 1/2. So we can now simply summarize what we have found here. So the integral over omega of exponential of minus psi of x divided by epsilon dx is exponential of the minimum of psi divided by epsilon, and then we have the sum. So we can always put a function here, let's call it g of x. So we have a sum of j at the point where psi achieves its minimum. This is 2 epsilon pi n over 2, the determinant of the SCN of psi at point pk, square root, and we sum over k from 1 to q. And this is plus a term here that is exponentially small. So this is the Laplace formula for a function j that is not 0. At the point pk, we assume that this is never 0. Alright, so this is an important calculation, because it reduces the calculation of this integral to a sum of the function psi at specific location. This is of course not completely trivial, because from a numerical point of view this requires to calculate the determinant here of the second derivative. And this formula, we are going to use it when we are going to approximate the integral in the calculation of the mean first passage time for a process to escape from a barrier. So I would like to finish with some references. One is the classical book of Bender and Orszag, Advanced Mathematical Methods for Scientists, in Springer. And there is also a nice a chapter at page 125 and 26 in the book of Jean Dieudonné, A Calcul Infinitesimal, which is in French.